Right, yeah. So let us proceed with this next topic. I mean, this application of Fourier transform, which is the amplitude modulation. So basically, amplitude modulation is a method that will be applied or shall be applied in communication, in which it is used in transferring low frequency signal over long range communication. Okay, so basically we have numbers of modulation techniques, which include the AM. We also have the FM. Yeah, we also have this PM, phase modulation. Okay, we also have another type of modulation, for instance, this PCM. So numbers of modulation. Basically, modulation is a method used to send a low frequency signal over a long range distance. Yeah. Okay, so in this particular case, we are going to see how this Fourier transform can be used to explain about this AM modulation technique. Yeah. Okay, so this is this graphical representation of signals relationship. Yeah, in AM application. Okay, MT basically is your information signal. Okay, XT is your high frequency signal. Basically, normally we're going to use a sine, sinusoidal or cosine signal. Okay, so MT, for example, is your voice of 4 kilohertz frequencies, low frequency value. So at the transmitter side, this information signal MT and this XT will be mixed. Yeah, will be mixed together, and this will produce the output of YT. Okay, YT is MT multiplied by XT, and then this signal will be transferred or will be transmitted using the antenna. Okay, and at the receiver side, going to receive the YT. Okay, so the receiver YT will be again mixed with the XT, in which XT and this XT are the same. Okay, so this is a condition that need to be fulfilled in your modulation. Yeah, in amplitude modulation, to be specific, in which this carrier signal, the XT carrier signal, need to be same at both transmitter and receiver part. So when we mix together or we multiply the output on the receive output of YT and the XT, we're going to get back the MT, which is the information signal. So that is how we obtain the information signal at the receiver side. Yeah. Okay, so this is about graphical representation of this AM system. So now we're going to see how this Fourier transform can be used to describe about the system's behavior. Yeah. Okay, this is the case where we have this M omega, which is a Fourier transform of your information MT. Okay, so we put it in a very simple representation. So M omega should be having a frequency value from negative omega M to positive omega M with the amplitude of 1. Okay, so we now transform the MT into frequency domain to the M omega. Okay, and from this equation at the transmitter side, we have the YT equals to MT multiplied with the XT. Yeah, MT is the information, XT is the carrier with the high frequency value. And as mentioned before, XT is always a sinusoidal signal. Yeah. Okay. So what we have here is that XT is having a frequency of omega C. Yeah. Omega C stands for the carrier frequencies. Yeah. So I put it straight away. I write straight away into a cosine terms or exponential terms. Yeah. So this is a cosine of omega CT. Okay. So we have multiplication of MT, and this exponential term will give us this form. Okay. YT will be half MT exponential j omega CT, okay, plus half MT exponential j negative j omega CT. Okay, so this YT, we can write this in terms of frequency domain, Fourier transform, in which YT will be written as Y omega. And from what we have learned in the frequency shifting properties, when a time domain multiplied with the exponential complex terms, we're going to have M omega minus omega C. Yeah. And also when the MT time domain signal multiply with exponential negative j omega C, so frequency shifting properties state that this results on M omega plus omega C. So this you can refer back to these frequency shifting properties. Yeah. So as a result, your y omega will be look like this. Okay, y omega is the output signal that will be transmitted by the antenna, the receiver side. So in terms of frequency response, it should be look like this, in which previously the m omega here will be shifted to the right by omega c and then shifted to the left by omega c frequencies. Okay, so note that the range for these signals here is from negative omega m to positive omega m, which is same as this. Yeah, same as this, right? The difference is that the signals initially, which is m omega, has been now shifted to the right and shifted to the left as a result of this mathematical representation. Yeah, so the output has been now reduced by half. Okay, so this is what happened at the transmitter side. Yeah, from this m omega information signal, we are now having y omega, which is also termed as modulated. Yeah, modulated signal, which will be transmitted using the antenna to the receiver side. Yeah. Okay. So this is what happened at the receiver side. So we're going to receive back this signal at the receiver side, which is transmitted by the transmitter and then received at the receiver. Yeah, this is the one. So we are now getting back. We are now to get back the empty. Yeah, that's our aim now. So we're going to show this by Fourier transform how we can get back the empty. Okay, so at the receiver side, if you can recall back at this diagram, received yt will be mixed with the xt, we will then produce the empty. Yeah. Okay, so what happened at the receiver side is that the empty can be obtained by a multiplication of the yt and the xt. This is what happened. Yeah. So again, we write the xt in terms of its exponential terms, a cosine. Yeah. Exponential j omega ct. Okay, and negative j omega ct. Okay, and further on, we're going to have mt will be yt and plus yt of this. Yeah, so just multiplication of this. Okay, and from this equation relates mt and yt, we can write it in terms of a Fourier transform, in which we're going to get the m omega. Okay, m omega, and this yt, which is multiplied with the exponential j omega ct, will be then returned to be half y omega minus omega c. Again, we are referring or we are using the frequency shifting properties. The same thing is applied for the second terms here. This will result on half y omega plus omega c. Yeah? Okay, again, we are referring to frequency shifting properties. Okay, so we need to consider back what happened at the transmitter side just now. Okay, at the receiver side, sorry, at the transmitter side, sorry, yeah. Okay, at the transmitter side, we have, yeah, at the transmitter side, yeah, Tx, we can recall that this y omega, okay, is equals to half of m omega minus omega c, okay, plus half m omega plus omega c. Okay, hopefully you can recall back, yeah, from the previous slide just now. Okay, this is what happened. Okay, y omega do have omega minus omega c and omega plus omega c. So I repeat it here. So if we substitute this condition, this equation into both of these terms, so omega, y omega minus omega c, y omega plus omega c, we are supposed to get this form of signal. Yeah, we're going to have m omega minus 2 omega c plus m omega, and then we have m omega, omega plus 2 omega c. So you can try this on your own, yeah, in which this is obtained from, we substitute these terms into y omega. Yeah, we substitute this term into y omega, so we're going to have these new terms here. So end up, we are supposed to get these empty, means that at the receiver side, your information signal m omega will be having these three different signals. We are going to have signals of m omega located between negative omega m to omega m. Then we have a second m omega, which is said to be shifted by 2 omega c to the right. And we also have m omega, which is said to be shifted by 2 omega c to the left. Okay, yeah? So this is what we're going to receive. Yeah, this is what we're going to receive at the receiver side. Yeah, but our interest is to get back this information signal between negative omega m and positive omega m, right? So what we need to do is that we need to filter out this part. In that we have to cut off this portion. To cut off this portion, we have to filter out anything beyond omega m and anything lesser than negative omega m. Okay, yeah? So due to this, in order for us to cut off the higher frequency part of 2 omega c and negative 2 omega c, what shall we do then is that we need to have a filters here. Okay, this is a filters that need to be used. Okay, this need to be used in which you are going to have a filters with these cut-off frequencies. Okay, and in order for us to retain this portion, yeah, this portion of signal between negative omega m to positive omega m, then your cutoff frequencies need to be equals to omega m, such that everything bigger than omega m will be filtered out, everything lower than negative omega m will be filtered out. So as such, when this h omega multiplied with this m omega, so end up we're going to have this original signal back, which is m omega value. Okay, so that's how we explain this AM modulation system by using a Fourier transform. Okay, so we have to choose the amplitude of your h omega, I mean amplitude of the filters responder B, such that you're going to get back the amplitude of 1 for the m omega. Yeah, so basically if you refer back to this, so since m omega equals to half, so your amplitude B need to be equals to 2, such that when you multiply these two values, you need to get back 1 as the amplitude. Yeah. Okay, any question on that so far? No, yeah, okay. So let us have a look at this example here. We are having a LTI, linear time invariant system model, shown in the diagram here. Okay. Sorry. Okay. The signal MT here is a multiplication of two signals, which are the VT and the CT. Okay, so I can write here straight away that the MT, okay, is equals to rectangular of T multiply with CT. Yeah, this is the one. CT is in terms of exponential terms. Okay. So you see that MT is now filtered by H omega to produce an output signal YT. So H omega is given here. That's your H omega, right? Basically, it's continuous, yeah, negative 20 to positive 20, and then 80 to 100, and so on, yeah. This is the train of impulses. So the train of rectangular functions, yeah, of H omega. Okay, so MT is said to be filtered by H omega to produce an output signal YT, and we are given the H omega. So the question number one is find the M omega. Okay, find the M omega. Okay, so how to find the M omega? The first thing is that we need to multiply. We know that the relationship of VT and CT will give us the MT based on this equation. Okay, MT is a rectangular T multiplied with CT. Yeah, and from this we can proceed with finding the M omega supposedly. And from the M omega obtained, we can sketch the spectrum of M omega. Okay, so I think let us proceed with the first two questions first, which is to find the M omega and sketch the spectrum of M omega. Yeah. Sorry for this. So let me share the Jamboard, the whiteboard. This, okay, let's proceed with this. Yeah. Right. So from your screen, I mean from your problem just now, we can write straight away that MT is equals to rectangular T multiplied with exponential J of 50T plus exponential negative, sorry, positive, yeah? Sorry, I need to put it positive here, sorry. Okay. Okay, J of 100T, okay, that should be the case. Okay, and we can write that this should be equals to rectangular T exponential J of 50T plus rectangular T exponential J of 100T. Okay, that should be the case. Okay, so from what we have learned in the previous lecture 10 and 11, okay, we know that rectangular T, okay, basically we can use a table, and this will give us Fourier transform of it as equal to sinc of omega divided by 2, yeah. So sinc omega divided by 2, yeah. This is a Fourier transform for the rectangular of T. So when we have rectangular T multiply with exponential j of 50t, so this is somehow related to the frequency shifting, and we have a sinc of omega minus 50 divided by 2, okay. And then we have a rectangular T of exponential j of 100t. So Fourier transform for this will be sinc of omega minus 100 divided by 2. So this is 2, sorry, this is 2 supposedly. Okay, so that should be your m omega, or I can say the Fourier transform for each of these individual terms. So for this, we can simply write that your m omega shall be equals to a sinc of omega minus 50 divided by 2 plus sinc omega plus, sorry, omega minus, yeah, suppose it is a minus, okay, minus 100 divided by 2. Okay, so this is our m omega obtained from previous mathematical work. Okay, so we need to sketch the spectrum. So we know that based on this, there should be two spectrum or two different spectrum for m omega, which is a sinc function which has been shifted by 50 units to the right, and also a sinc function which has been shifted by 100 units to the right. So as such, we can sketch that the m omega should look like this. Okay, that should be your m omega. Okay, so we're going to have a sinc function. We have learned a sinc function, yeah, in lecture number 2, I believe. So this is 50, a shift by 50 units to the right, and then we also have another sinc function, okay, which is shifted by 100 units to the right. So that should be the spectrum of your m omega, which is basically two sinc function. The first one is a sinc function shifted by 50 units to the right. Second one is a sinc function but now shifted by 100 units to the right. So that should be your m omega. So this answers the first and second questions for our example just now. Yeah? Okay, so let's go back to the question. Okay, so for this example, number 3, what is the role of H omega? So H omega is a filter, yeah? H omega is a filter. Let's know that H omega should be a filter. It's understood. Okay, number 4, sketch the spectrum of Y omega. Right, so from what we have learned before, you have the m omega consists of two sinc function, yeah. If I can re-sketch it for you here, that's your m omega. Okay, we have, yeah, this is at 50, and we have another one which is at 100. Okay, so that should be the m omega, yeah, this two position. So y omega, which is your output, can be obtained by multiplication with the between m omega and h omega. Yeah, so means that we have to multiply the m omega that we have obtained previously with this h omega. So if we multiply these two, we can see that a signal with the 50 frequencies will be located somewhere between 20 and 80, in which it will produce a value of 0. Yeah, because between 20 and 80, the amplitude is 0. So when we multiply the m omega and the h omega, it will give us 0. But for the second sinc function, which is at 100, knowing that h omega for this rectangle train, it will be somehow proceed up to 120. Okay, we can know that if you multiply this m omega and the h omega somehow this sinc function will somewhere located in between 80 and 120. So if I can sketch it for you, you're going to have this sinc function will be located somewhere in between 80 and 120. So your spectrum for H omega, sorry, spectrum of Y omega, okay, if I can sketch this for you, due to this multiplication of two signals, you're going to have at 100 and at negative 100, okay, that should be two sinc function. Okay, that should be the case. Sorry, yeah, not that nice, my drawing, but hopefully you understand that, yeah. So that should be my output spectrum of Y omega. So we know that H omega equals to 2. M omega just now, what should be the value for M omega? I forgot to record the value of M omega. Okay, it's equals to 1, yeah? M equals to 1. So we have this is equals to 1. Okay, so basically we have 2, so the output for Y omega equals to 2. Okay, yeah? So that should be your Y omega terms, okay? And in terms of the number 5, which is to find the YT, okay, YT. So based on this, we know that, sorry, I apologize, I made mistakes, sorry for that, yeah, because my M omega is only located at 50 and 100. There is no M omega at the negative side. So this part basically does not exist. I need to, sorry for this, sorry, yeah. Okay, I need to cancel this. Sorry for that, it's my mistake. We only have a sinc function at positive 100 only. So that should be the only sinc function that will exist for your Y2 omega, yeah? Okay, hopefully you understand this clearly. Yeah? Sorry for this misunderstanding. Okay, so from the mathematical equation, I mean from this diagram, you know that your Y omega equals to 2 sinc function of omega minus 100 divided by 2. It's understood, yeah, based on this diagram. So we can do the inverse Fourier transform. We're going to get the YT, and this will give us, inverse Fourier transform will give us 2 rectangular of t, and this will give us exponential j of 100t. Again, this is based on frequency shifting properties, yeah? Okay, so your YT in time domain will be look like this. Okay. Any question on this example, on this application of Fourier transform? No? Okay, this is the last example for lecture 12. I'm not going to do this. Again, I will request you to solve this on your own to ensure that you really understand what I've taught in class just now. Okay, so try to solve this on your own. If you got problem with this, so always you always discuss with me, yeah, all these issues. Okay, so that's all for lecture 12, and that's all for chapter 3 on Fourier transform. So hopefully you understand well on Fourier transform, in which we have learned about the properties in lecture 10 and 11, and afterwards we have applied the Fourier transform in solving or in understanding few properties, which include the filters and also the amplitude modulation. Okay, any question before we end the class today? Any question before we end the class today?